It's time we started solving differential equations. This is the third lecture of the term, and I have yet to solve a single differential equation in this class. Well, that will be rectified from now till the end of the term. So once you learn separation of variables, which is the most elementary method there is, I think the single most important equation is the one that's called the first order linear equation, both because it occurs frequently in models, because it's solvable, and I think that's enough. If you drop the course after today, you'll still have learned the two important methods, separation of variables and first order linear equations. So what does such an equation look like? Well, I'll write it in, there are several ways of writing it, but I think the most basic is this. I'm going to use x as the independent variable because that's what your book does, but in the applications it's often t, time, that's the independent variable, and I'll try to give you examples which show that. So the equation looks like this. Some function of x times y prime plus some other function of x times y is equal to yet another function of x. Obviously the x doesn't have the same status here that y does, so y is extremely limited how it can appear in the equation, but x can be pretty much arbitrary in those places. So that's the equation we're talking about, and I'll put it up. This is the first version of it, and we'll call them purple. Now, why is that called a linear equation? The word linear is a very heavily used word in mathematics, science, and engineering. For the moment, the best simple answer is because it's linear in y and y prime, the variables y and y prime. Well, y prime is not a variable. Well, you'll learn in a certain sense it helps to think of it as one, not right now perhaps, but think of it as linear by the most closely analogous thing would be the equation, a linear equation that looked like a real linear equation, the kind you studied in high school, which would look like this. It would have two variables and I guess constant coefficients equal c. Now that's a linear equation, and that's the sense in which this is linear. It's linear in y prime and y, which are the analogs of the variables y1 and y2. A little bit of terminology. If c is equal to 0, it's called homogeneous. The same way this equation is called homogeneous, as you know from 1802, if the right-hand side is 0. So c of x I should write here, but I won't. That's called homogeneous. Now, this is a common form for the equation, but it's not what's called standard form. The standard form for the equation, and since this is going to be a prime course of confusion, which is probably completely correct, but a prime source of confusion is what I meant. The standard linear form, and I'll underline linear, is the first coefficient of y prime is taken to be 1. So if I divide, you can always convert that to a standard form by simply dividing through by it. And if I do that, the equation will look like y prime plus. Now, it's common to not call it b anymore, the coefficient, because it's really b over a. And therefore, it's common to adopt yet a new letter for it. And the standard one that many people use is p. How about the right-hand side? We need a new letter for that, too. It's c over a, but we'll call it q. So when I talk about the standard linear form for a linear first-order equation, it's absolutely that I'm talking about. Now, you immediately see there's a potential for confusion here, because what did I call the standard form for a first-order equation? So I'm going to say not this. The standard first-order form what would that be? Well, it would be y prime equals and everything else on the left-hand side. So it would be y prime, and now if I turn this into the standard first-order form, it would be negative p of x, y, plus q of x, but of course nobody would write negative p of x, so now I explicitly want to say that this is a form which I will never use for this equation, although half the books in the world do. In short, this poor little first-order equation belongs to two ethnic groups. It's both a first-order equation, and therefore its standard form should be written this way, but it's also a linear equation, and therefore its standard form should be used this way. Well, it has to decide, and I have decided for it. It is above all a linear equation, not just a first-order equation, and in this course, this will always be the standard form. Now, well, what on earth is the difference? Oh, if you don't do it that way, the difference is entirely in the sign of p, but if you get the sign of p wrong in the answers, it's just disaster from that point on. A trivial little change of sign in the answer produces solutions and functions which have totally different behavior, and you're going to be really lost in this course. So maybe I should draw a line through it to indicate, please don't pay any attention to this whatsoever. Except that we're not going to do that. Okay? Well, what's so important about this equation? Well, number one, it can always be solved. That's a very, very big thing in differential equations. But it's also the equation which arises in a variety of models. Now, I'm just going to list a few of them. All of them, I think, you will meet in either in part one or part two of problem sets over these first couple of problem sets, or second and third maybe. But of them, I'm going to put at the very top of the list what I'll call here, I'll give it two names, the temperature diffusion model. Well, I'm sorry, it would be better to call it temperature concentration by analogy. Temperature concentration model. There's the mixing model, which is hardly less important. In other words, it's almost as important. You have that on your problem set. And then there are other slightly less important models. There's a model of radioactive decay. There's a model of a bank interest, bank account. Various motion models. You know, Newton's law type problems, if you can figure out a way of getting rid of the second derivative. Some motion problems. A classic example is the motion of a rocket being fired off, et cetera, et cetera, et cetera. Now, today I have to pick a model, and the one I'm going to pick is this temperature concentration model. So this is going to be today's model. Tomorrow's model in the recitation, I'm asking the recitations to, among other things, make sure they do a mixing problem. To show A, to show you how to do it, and B, because it's on the problem set, so that's not a good reason, but it's not a bad one. The others are either in part 1 or we'll take them up later in the term. This is not going to be the only lecture on the linear equation. There'll be another one next week of equal importance, but we can't do everything today. So let's talk about the temperature concentration model, except I'm going to change its name to the conduction diffusion model. I'll put conduction over there and diffusion over here, let's say. Since, as you'll see, the similarities, or they're practically the same model, all that's changed from one to the other is the name of the ideas. In one case you call it temperature, and the other case you call it concentration, but the actual mathematics isn't identical. So let's begin with conduction. All right, here's so I need a simple physical situation that I'm modeling. So imagine a tank of some liquid. Water will do as well as anything. And in the inside is a suspended somehow is a chamber. A metal cube will do. And let's suppose that its walls are partly insulated. Not so much that no heat can get through. There is no such thing as perfect insulation anyway, except maybe a perfect vacuum. Now, inside, so here on the outside is liquid. Okay. On the inside is what I'm interested in is the temperature of this thing. I'll call that T. Now, that's different from the temperature of the external water bath, so I'll call that T sub E. T for temperature, measured in Celsius, let's say, for the sake of definiteness. But this is the external temperature, so I'll indicate it with an E. Now, what is the model? Well, in other words, how do I set up a differential equation to model this situation? Well, it's based on a physical law, which I think you know. You've had simple examples like this. The so-called Newton's law of cooling. Which says that the rate of change, the temperature, the heat goes from the outside to the inside by conduction only. Heat, of course, can travel in various ways: by convection, by conduction as here, or by radiation are the three most common. Of these, I only want one, namely transmission of heat by conduction. And that's the way it's probably a little better to call it the conduction model rather than the temperature model, which might be involve other ways for the heat to be traveling. So dt, the independent variable, is not going to be x as it was over there. It's going to be t for time. So let's maybe I should write that down. T equals time. Capital T equals temperature in degrees Celsius, so you put in the degrees Celsius if you want. So it's proportional to the temperature difference between these two. Now, how shall I write the difference? Write it this way, because if you don't, you'll be in trouble. Now, why do I write it that way? Well, I write it that way because I want this constant to be positive, a positive constant. In general, any constants or parameters which are physical, have some physical significance, one always wants to arrange the equation so that they're positive numbers, the way people normally think of these things. This is called the conductivity. The conductivity of what? Well, I don't know, of the system, of the situation. The conductivity of the wall, or if the metal were just by itself, it would, at any rate, it's a constant. It's thought of as a constant. And why positive? Well, because if the external temperature is bigger than the internal temperature, I expect T to rise, the internal temperature to rise. That means dt, its slope, should be positive. So in other words, if TE is bigger than T, I expect this number to be positive. And that tells you that K must be a positive constant. If I had turned it the other way, expressed the difference in the reverse order, K would then be negative, have to be negative in order that this turn out to be positive in that situation I described. And since nobody wants negative values of K, you have to write the equation in this form rather than the other way around. So there's our differential equation. It will probably have an initial condition, so it could be the temperature at the starting time should be some given number T0. But the condition could be given another way. One could ask, what's the temperature as time goes to infinity, for example? There are different ways of giving that initial condition. Okay, that's the conduction model. What would the diffusion model be? The diffusion model mathematically would be word for word the same. The only difference is that now what I imagine is, I'll draw the picture the same way, except now I'm going to label the inside not with a T but with a C. C for concentration. It's in an external water bath, let's say. So there's an external concentration. And what I'm talking about is some chemical, let's say salt will do as well as anything. So C is equal to salt concentration inside, and CE would be the salt concentration outside in the water bath. Now, I imagine some mechanism. So this is a salt solution, that's a salt solution, and I imagine some mechanism by which the salt can diffuse. It's a diffusion model now. Diffuse from here into there, or possibly out the other way, and that's usually done by vaguely referring to that the outside is a semi-permeable membrane. Semi-permeable so that the salt will have a little hard time getting through, but permeable so that it won't be blocked completely. So there's a membrane, you write the semi-permeable membrane outside the inside. Well, I give up. You know, not membrane somewhere. Sorry. Membrane wall. How's that? Now, what's the equation? Well, the equation's the same, except it's called the diffusion equation. I don't think Newton got his name on this. The diffusion equation says that the rate at which the salt diffuses across the membrane, which is the same up to a constant as the rate at which the concentration inside changes, is some constant, usually called K still. Okay. Do I contradict? Yeah, okay. Let's keep calling it K1. Now it's different. Times CE minus C. And for the same reason as before, if the external concentration is bigger than the internal concentration, we expect salt to flow in. That will make C rise. It will make this positive, and therefore we want K to be positive, just K1 to be positive for the same reason it had to be positive before. So in each case, the model that I'm talking about is the differential equation. So maybe I should let's make that clear. Or I would say that this first order differential equation models this physical situation, and the same thing is true on the other side over here. This is the diffusion equation, and this is the conduction equation. Now, if you were in any doubt about the power of differential equations, the point is, when I talk about this thing, I don't have to say which of these I'm following. I'll use neutral variables like y and x to solve these equations, but clearly with a single stroke, I will be handling both situations together, and that's the power of the method. Now, you obviously must be wondering, look, hey, these look very, very special. He said he was going to talk about the general first-order equation, but these look rather special to me. Well, not too special. How shall we write it? Suppose I'll write it let's take the temperature equation just to have something definite. Notice that it's in a form corresponding to Newton's law, but it is not in the standard linear form. Let's put it in standard linear form, so at least you can see that it's a linear equation. So if I put it in standard form, it's going to look like dt dt, d little t, plus kt is equal to k times te. Now compare that with the way the general equation is supposed to look, that yellow box over there, the standard linear form. How are they going to compare? Well, this is a pretty general function. This is a general function of t, because, you know, I can make the external temperature, I can suppose it behaves in any way I like. Steadily rising, decaying exponentially, maybe oscillating back and forth for some reason. The only way in which it's not general is that this k is a constant. So I will ask you to be generous. Let's imagine the conductivity is changing over time. So this is usually constant, but there's no law which says it has to be. How could a conductivity change over time? Well, we could suppose, for example, that this wall was made of slowly congealing jello, for instance. You know, it starts out as liquid, then it gets solid, and jello doesn't transmit heat, I believe, quite as well as liquid does, as a liquid would. Is jello a solid or a liquid? I don't know. That's let's forget about that. So with this understanding, so let's say not necessarily here, but not necessarily, I can think of this, therefore, by allowing k to vary with time and the external temperature to vary with time. I can think of it as a general linear equation. So these models are not special, they're fairly general. Well, I did promise you I would solve an equation, and in this lecture I still have not solved any equations. Okay, time to stop temporizing and solve. So I'm going to, in order not to play favorites with these two models, I'll go back to, and to get you used to thinking of new variables all the time. That is, you know, being eclectic, switching from one variable to another according to which particular lecture you happen to be sitting in. So let's take our equation in the form y prime plus p of xy, the general form, using the old variables, equals q of x. Solve me. Well, there are different ways of describing the solution process. No matter how you do it, it amounts to the same amount of work. And there's always a trick involved in each one of them, since you can't suppress a trick by doing the problem some other way. The way I'm going to do it, I think, is the best. That's why I'm giving it to you. It leads to, it's the easiest to remember, leads to the least work, but I have colleagues who would fight with me on that point. So since they're not here to fight with me, I am free to do whatever I like. One of the main reasons is that of doing it the way I'm going to do is because I want you to get one more word into your consciousness, and that's the word, two words, integrating factor. I'm going to solve this equation by finding an integrating factor of the form u of x. What's an integrating factor? Well, I'll show you, not by writing an elaborate definition on the board, but showing you what its function is. It's a certain function u of x. I don't know what it is, but here's what I want it to do. I want to multiply, I'm going to drop the x's just so that the thing looks less complicated. So what I want to do is multiply this equation through by u of x. That's why it's called a factor, because you're going to multiply everything through by it. So it's going to look like uy prime plus p u y equals qu. And now this thing is, so far it's just a factor. What makes it an integrating factor is that this, after I do that, I want this to turn out to be the derivative of something with respect to x. You see the motivation for that? If this turns out to be the derivative of something because I've chosen u so cleverly, then I'll be able to solve the equation immediately just by integrating this with respect to x and integrating that with respect to x. You just then integrate both sides with respect to x, and the equation is solved. Now, the only question is, what should I choose for u? Well, if you think of the product formula, there might be many things to try here, but there's only one reasonable thing to try. Try to pick u so that it's the derivative of u times y. See how reasonable that is. If I use the product rule on this, the first term is u times y prime. The second term would be u prime times y. Well, I've got the y there, so this will works if what? If, what's the condition that u must satisfy in order for that to be true? Well, it must be that after I do the differentiation, u prime turns out to be p times u. So is it clear? This is something we want to be equal to, and the thing I'll try to do it is by choosing u in such a way that this equality will take place, and then I'll be able to solve the equation. And now, so here's what my u prime must satisfy. Hey, we can solve that, but please don't forget that p is p of x. It's a function of x. So if you separate variables, I'm going to do this. So what is it? du over u equals p of x times dx. If I integrate that, so separate variables, integrate, and you're going to get du over u integrates to be the log of u, and the other side integrates to be the integral of p of x dx. And you can put an arbitrary constant there, or you can think of it as already implied by the indefinite integral. Well, that doesn't tell us yet what u is. What should u be? Notice I don't have to find every possible u which works. All I'm looking for is one. All I want is a single u which satisfies that equation. Well, u equals the integral e to the integral of p dx. That's not too beautiful looking, but by differential equations, things can get so complicated that by the, in a week or two, you will think of this as an extremely simple formula. So there's the formula for our integrating factor. We found it. We'll always be able to write an integrating factor. Don't worry about the arbitrary constant because you only need one such u. So no arbitrary constant since only one u needed. And that's the solution, the way we solve the linear equation. Okay, let's take over and actually do it. I think it would be better to summarize it as a clear-cut method. So let's do that. So what's our method? It's the method for solving y prime plus py equals q. Well, the first place, make sure it's in standard linear form. If it isn't, you must put it in that form. Notice the formula for the integrating factor. The formula for the integrating factor involves p, the integral of p dx, so you better get the right p. Otherwise, you're sunk. Okay, so put it in standard linear form. That way you'll have the right p. Notice that if you wrote it in that form, and all you remembered was integral e to the integral p dx, the p would have the wrong sign. That, if you're going to write that, p should have a negative sign there. So do it this way and no other way. Otherwise you'll get confused and get wrong signs, and as I say, that will produce wrong answers, and not just slightly wrong answers, but disastrously wrong answers from the point of view of the modeling, if you really want answers to physical problems. So here's a standard linear. Then find the integrating factor. So calculate e to the integral p dx, the integrating factor. And then multiply both. I'm putting this as both. Underline that as many times as you have room in your notes. Multiply both sides by this integrating factor by e to the integral p dx. And then integrate. Okay, let's take a simple example. Suppose we started with the equation xy prime minus y equals, I had a x squared, x cubed, something like that. X cubed, I think. Yeah, x cubed. Okay. What's the first thing to do? Put it in standard form. So step 0 will be to write it as y prime minus 1 over x times y equals x squared. There are two standard errors. Let's do the work first, and then I'll talk about mistakes. And now what? Well, we now calculate the integrating factor. So that's, I would do it in steps. You can integrate negative 1 over x, right? That integrates to minus log x. So the integrating factor is e to the integral of this dx. So it's e to the negative log x. Now in real life, that's not the way to leave that. What is e to the negative log x? Well, think of it as e to the log x to the minus 1. Or in other words, it is e to the log x is x. So it's x to the minus, so it's 1 over x. So the integrating factor is 1 over x. Okay, multiply both sides by the integrating factor. Both sides of what? Both sides of this, the equation written in standard form, and both sides. So it's going to be 1 over x y prime minus 1 over x squared y is equal to x squared times 1 over x, which is simply x. Now, if you have done the work correctly, you should be able now to integrate the left-hand side directly. So I'm going to write it this way. I always recommend that you put in as an extra step, well, I won't. Put in as an extra step the reason for using that integrating factor. In other words, that the left-hand side is supposed to be now 1 over x times y prime. I always put in that because there's always a chance you made a mistake or forgot something. Look at it, mentally differentiate it using the product rule just to check that in fact it turns out to be the same as the left-hand side. So what do we get? 1 over x times y prime plus y times the derivative of 1 over x, which indeed is negative 1 over x squared. And now finally, that's 3a. Continue, do the integration. So you're going to get let's see if we can do it all on one board. 1 over x times y is equal to x plus a constant, x squared over 2 plus a constant. And the final step will be, therefore, I now want to isolate y by itself. So y will be equal to, multiply through by x cubed over 2 plus c times x. And that's the solution. Okay, let's do one a little slightly more complicated. Let's try this one. Now my equation is going to be 1. I'll still keep 2, y and x as the variables. I'll use t in a minute or two. 1 plus cosine x. So I'm not going to give you this one in standard form either. Trick question. Y prime minus sine x times y is equal to anything reasonable, I guess. I think what x 2x. Make it more exciting. Okay. Now, I think I should warn you where the mistakes are, just so that you can make all of them. So this is mistake number 1. You don't put it in standard form. Mistake number 2, generally people can do step 1 fine. Mistake number 2 is you don't. This is my most common mistake, so I'm very sensitive to it. But that doesn't mean if you make it, you'll get any sympathy from me. I don't give sympathy to myself. You're so intent on, so happy at having found the integrating factor, you forget to multiply q by the integrating factor also. You just handle the left-hand side of the equation, and you forget about the right-hand side. So the emphasis on the both here is the right hand, please include the q. Please include the right-hand side. Any other mistakes? Well, nothing that I can think of. Well, maybe only. Anyway, we're not going to make any mistakes for the rest of this lecture. So what do? We write this in standard form. So it's going to look like y prime minus sine x divided by 1 plus cosine x times y equals, my heart sinks because I know I'm supposed to integrate something like this, and boy, that's going to give me problems. Okay, well, not yet. What's the integrating factor? The integrating factor is, well, we want to calculate the integral of negative sine x over 1 plus cosine. That's the integral of p dx. And after that, we have to exponentiate it. Well, can you do this? Yeah, but if you stare at it a little while, you can see that the top is the derivative of the bottom. That is great. That means it integrates to be the log of 1 plus cosine x. Is that right? 1 over 1 plus cosine x times the derivative of this, which is negative cosine x. Therefore, the integrating factor is e to that. In other words, it is 1 plus cosine x. Therefore, so this was step 0. Step 1, we found the integrating factor. And now step 2, we multiply through by the integrating factor. And what do we get? We multiply through the standard form equation by the integrating factor. And if you do that, what you get is, well, y prime gets the coefficient 1 plus cosine x. Y prime minus sine x equals 2x. Oh dear. Well, I hope somebody would giggle at this point. What's giggleable about it? Well, that all this was totally wasted work. That's called spinning your wheels. No, it's not spinning your wheels. It's doing what you're supposed to do and finding out that you wasted the entire time doing what you were supposed to do. Well, we get, in other words, the net effect of this is to end up with the same equation we started with. But what is the point? The point of having done all this was because now the left-hand side is exactly the derivative of something, and the left-hand side should be the derivative of what? Well, it should be the derivative of 1 plus cosine x times y, all prime. Now, you can check that that's in fact the case. It's 1 plus cosine x, y prime, plus minus sine x, the derivative of this side, times y. So, if you had thought, in looking at the equation, to say to yourself, this is the derivative of that, maybe I'll just check right away to see if it's the derivative of 1 plus cosine x sine y, you would have saved that work. Well, you don't have to be brilliant or clever or anything like that. You do it, you can follow your nose, and it's just, I want to give you a positive experience in solving linear equations, not too negative. Anyway, so we got to this point. So this is 2x, and now we're ready to solve the equation, which is, the solution now will be 1 plus cosine x times y is equal to x squared plus a constant, and so y is equal to x squared divided by x squared plus a constant divided by 1 plus cosine x. Suppose I had given you an initial condition, which I didn't, but suppose the initial condition said that y is 0 were 1, for instance. Then the solution would be, so this is an if, I'm throwing in at the end just to make it a little bit more of a problem. How would I then I could evaluate the constant by using the initial condition. What would it be? This would be, on the left-hand side, 1. On the right-hand side would be c over 2. So I would get 1 equals c over 2. Is that correct? Cosine of 0 is 1, so that's 2 down below. Therefore, c is equal to 2, and that would then complete the solution. It would be x squared plus 2 over 1 plus cosine x. Now, let's, you can do this in general, of course, and get a general formula, and we'll have occasion to use that next week. But for now, why don't we concentrate on the most interesting case, namely that of the linear equation with constant coefficient. That is, so let's look at the linear equation with constant coefficient, because that's the one that most closely models the conduction and diffusion equations. So what I'm interested in is, since this is of them all, probably the most important case is the one where p is a constant, because of its application to that, and many of the other, the bank account, for example, all of those would use a constant coefficient. So how is the thing going to look? Well, I'll use the cooling. Let's use the temperature model, for example. The temperature model, the equation will be dt dt plus kt is equal to, now notice on the right hand side, this is a common error, you don't put TE, you have to put KTE, because that's what the equation says. If you think units, you won't have any trouble. Units have to be compatible on both sides of a differential equation, and therefore whatever the units were for capital KT, I'd have to have the same units on the right hand side, which indicates I cannot have KT on the left of the differential equation and just T on the right and expect the units to be compatible. That's not possible. So that's a good way of remembering that if you're modeling temperature or concentration, you have to have the K on both sides. Okay, let's do, now a lot of this we're going to do in our head now because this is really too easy. What's the integrating factor? Well, the integrating factor is going to be the integral of K, the coefficient now is just K, P is a constant K, and if I integrate K dt, I get KT, and I exponentiate that, so the integrating factor is e to the KT. I multiply through both sides, multiply by e to the KT, and what's the resulting equation? Well, it's going to be, I'll write it in the compact form, it's going to be e to the KT times t, all prime, the differentiation now, of course, is with respect to the time, and that's equal to k t e, whatever that is, times e to the kt. This is a function of t, of course, the function of little time. Sorry, little t time. Okay, and now finally we're going to integrate. What's the answer? Well, it is e to the, so we're going to get e to the kt times t is, sorry, k little t, k times time times the temperature is equal to the integral of k te, I'll put the fact that it's a function of t inside just to remind you, e to the kt, and now I'll put the arbitrary constant. Let's put in the arbitrary constant explicitly. So what will t be? Okay, t will look like this finally. It will be e to the negative kt, that's on the outside. Then you will integrate. Of course, the difficulty of doing this integral depends entirely upon how this external temperature varies. But anyway, it's going to be k times that function which I haven't specified, e to the kt, plus c times e to the negative kt. Now, some people, many in fact, and almost always in the engineering literature, almost never write indefinite integrals, because an indefinite integral is indefinite. In other words, this covers not just one function, but a whole multitude of functions which differ from each other by an arbitrary constant. So in a formula like this, there's a certain vagueness, and it's further compounded by the fact, I don't know whether to put whether the arbitrary constant is here. I seem to have put it explicitly on the outside the way you're used to doing from calculus. Many people therefore prefer, and I think you should learn this, to do what is done in the very first section of the notes called definite integral solutions. They like, if there's an initial condition saying that the internal temperature at time 0 is some given value, what they like to do is make this thing definite by integrating here from 0 to t, and making this a dummy variable. You see what that does is it gives you a particular function, whereas it was a, I'm sorry I didn't put in the dt one, woo, minus 2. What it does is that when time is 0, all this automatically disappears, and the arbitrary constant will then be, well, it's t, so in other words, c times this, which is 1, is then equal to t. In other words, if I make this 0, then I can write c as equal to this arbitrary starting value. Now, when you do this, the essential thing, and we're going to come back to this next week, but right away, that because k is negative, is positive, I wanted, since I emphasized that so much at the beginning of the period, I want to conclude by showing you what its significance is. This part disappears because k is positive, the conductivity is positive, this part disappears as t goes to 0. This goes to 0 as t goes to infinity. So this is the solution that remains. This, therefore, is called the steady state solution. The thing which the temperature behaves like as t goes to infinity. This is called the transient because it disappears as t goes to infinity. It depends on the initial condition, but it disappears, which shows you that in the long run, for this type of problem, the initial condition makes no difference. The function behaves always the same way as t goes to infinity.